Back in 1971, a few atomic clocks went on a trip around the entire world. Now, I know that sounds like something straight out of a sci-fi movie, but this was a real-life experiment, and it was designed to solve one of the biggest puzzles in physics.
But before we get into that, let me ask you a simple question. Do you think time passes at the exact same rate for someone standing still on the ground as it does for someone flying 30,000 feet up in a jet? I mean, it seems obvious, right? A second is a second, no matter where you are. But what if I told you that for almost 100 years, that very question was the subject of a fierce scientific debate?
In fact, the journal Science went so far as to call it one of the most enduring scientific debates of the entire 20th century. They called it the clock paradox. It was this mind-bending puzzle that came directly out of Einstein's theory of relativity. And for decades, it was just something people argued about. It was all theory. But that was about to change, thanks to one very bold experiment.
Yeah, this whole debate led to a pretty wild plan. A full-blown, around-the-world test that was designed to finally, once and for all, settle the score. So here was the plan, cooked up by two physicists, Hafele and Richard Keating. It was actually beautiful in its simplicity. In October of 1971, they were going to take 4 super accurate cesium atomic clocks, buy them tickets on regular old commercial jets, and fly them all the way around the world. They'd do one trip flying east and another trip flying west. And the whole mission? To see if the clocks that flew came back showing a different time than the identical clocks they left behind on the ground.
And you know, the stakes here were incredibly high. This wasn't just some fun little side project. They were trying to achieve what they called an unambiguous empirical resolution. In other words, they wanted to end all the arguments with cold, hard data. No more paradoxes, just proof.
Now, to understand what they expected to find, we've got to look at 2 competing effects from Einstein's theories. These 2 ideas were essentially in a race against each other, both messing with the clocks at the same time.
Okay, so on one side of this tug-of-war, you've got special relativity. That's the one that deals with speed, and it basically says the faster you move through space, the slower you move through time. But on the other side, you have general relativity, which is all about gravity. And it says the weaker the gravity, the faster your clock ticks. So the clocks on the plane were going to get hit by both of these effects at once, pulling time in opposite directions. So here's the crucial part. The direction they flew mattered. A lot. When the plane flew eastward, it was moving with the Earth's rotation. So its total speed was its own airspeed plus the speed of the planet's spin. That extra speed, according to special relativity, should make its clock tick slower, causing it to actually lose time. But flying westward, that's going against the spin, which subtracts from its overall speed, and should cause it to gain time compared to the clock on the ground. That's the speed effect, what they called the kinematic effect. But don't forget the other player in this game, the gravitational effect. Because the planes are flying way up at high altitude, they're farther from the Earth's center, which means gravity is just a tiny bit weaker up there. And general relativity predicts this should cause the clocks to speed up and gain time. And here's the key. It would do this no matter which direction they were flying.
So, which one wins? How do these 2 effects battle it out? Well, check out this graph from their original paper. It shows the prediction perfectly. For the eastward trip over there on the right, the time loss from all that extra speed was expected to be stronger than the time gain from altitude. The result? A net loss of time. But for the westward trip, on the left, the time gain from reduced speed would add to the time gain from altitude, creating a prediction for a much bigger gain in time. And here are the actual numbers they crunched. For the eastward trip, they predicted a net loss of about 40 nanoseconds. And for the westward trip, they predicted a net gain of a whopping 275 nanoseconds. The theory made a very clear, a very testable, and let's be honest, a very weird prediction. A clock's time literally depends on the path it takes through space-time.
So with the predictions all set and the theory laid out, there was only one thing left to do. Fly the clocks and see what they said when they got back. This was it, the moment of truth.
But of course, there was a huge practical problem. I mean, these atomic clocks were the best in the world, but they weren't perfect. They could still drift a little bit. And the scientists themselves noted that the clocks were prone to, and I'm quoting here, unpredictable changes in rate. Not exactly what you want to hear when you're measuring nanoseconds.
And just look at this. This is what the raw data from the 4 individual clocks actually looked like. It is a complete mess. The lines are all drifting away from each other. If they had only flown 1 or 2 clocks, all of that random noise would have completely drowned out the tiny relativistic effect they were hunting for.
But here's where their idea was so brilliant. Their solution was to take the average of all 4 clocks. The thinking was that all that random noise would just cancel itself out. And here it is. This is the smoking gun. On the left, you see a crystal clear step down after the eastward trip. That's a time loss. And on the right, a much bigger step up after the westward trip, a time gain. The crazy prediction was right there in the data, clear as day.
So, the final measured result for that eastward journey? A loss of 59 nanoseconds.
And for the westward journey, a gain of 273 nanoseconds.
Okay, let's put it all together on the final scorecard. Theory versus reality. For the eastward trip, the prediction was a loss of 40 nanoseconds. What they observed was a loss of 59. Pretty close. But look at the westward trip. Predicted, a gain of 275 nanoseconds. Observed, a gain of 273 nanoseconds. I mean, that is absolutely stunning. Within their margins of error, Einstein's strange predictions were completely confirmed.
So, the verdict was in. This scientific detective story had finally reached its conclusion.
The experiment was a resounding success. It gave them exactly what they'd set out to find, that unambiguous empirical resolution to the clock paradox. They had proven, with real-world objects you could hold in your hands, that time is, in fact, relative.
And I just love how they put it in their final paper. They delivered the final word on the debate, saying there seems to be little basis for further arguments about whether clocks will indicate the same time after a round trip, for we find that they do not. Case closed.
So, okay, this was all proven more than 50 years ago. But it's not just some dusty old historical curiosity. The global positioning system, the GPS that your phone uses every single day, it only works because its software is constantly correcting for these exact same relativistic effects. The satellites are moving incredibly fast and they're in a weaker gravitational field, just like those clocks on the plane. Seriously, without correcting for relativity, your GPS would be off by miles within a single day. So the next time you use a map on your phone, just remember the clocks that flew around the world to prove that time itself depends on your journey.